All right, today we are going to talk about 9.3. We're going to be testing the difference between two means when we have dependent samples. So in 9.1, we did independent samples and we did a z-test. But for dependent samples, this is when the subjects are paired or matched in some way. It's also called a matched pair sample. And we have to use a t-test. So this is a situation. So suppose a medical researcher wants to see whether a drug will affect the reaction time of its users. To test this hypothesis, the researcher must pre-test the subjects in the sample. That is, they are given a test to ascertain their normal reaction times, then after taking the drug, the subjects are tested again using a post-test. Finally, the means of the two tests are compared to see whether there is a difference. Since the same subjects are used in both cases, the samples are related. Subjects scoring high on the pretest will generally score high on the post-test, even after consuming the drug. Likewise, those scoring lower will tend to score lower. To take this effect into account, we employ a t-test using the differences between the pretest values and the post-test values. So again, the gain or loss in values is compared. So we have to use the t-test because these samples are dependent. So some other examples of dependent situations, does an ACT prep course raise test scores? Does a counseling program help subjects lose weight? Okay, so subjects can be matched or paired according to a variable. A study involving learning, subjects could be paired according to their IQs. So matching helps reduce a type 2 error by eliminating extraneous variables. So again, we can eliminate some extraneous variables, but we're not eliminating all. So when subjects are matched according to one variable, the matching process does not eliminate the influence of other variables. When the same subjects are used for a pre-post study, sometimes the knowledge that they are participating in a study can influence the results. So in the first case, like we match them based on IQs, but that doesn't affect like you could have the variables where they're a really good reader versus math person, that could take into account how they score. Okay, so our hypotheses, we're going to use mu sub d. So d is going to be the expected mean of the difference of the matched pairs. So your difference is assumed to be 0, so that there's no difference between the two means. Or the alternative hypothesis is not equal to 0, or less than 0, or greater than 0. The assumptions for two means when the samples are dependent. The sample or samples are random. They are dependent, and they are normally distributed. This is our formula. With this formula, there's a little bit more involved in finding these. So we're going to have to find standard deviation, there's a whole lot going on there. So we're going to have a table view to help calculate that. But it's still the sample mean. So D bar is the sample difference, the mean. So you add up all the D's, all the differences, and divide them by N. So that's our average. And then minus mu sub D. And remember, mu sub D is assumed to be 0. And then standard deviation divided by square root of N. Okay, so this is the process, same process, but when we compute the test value, there's several things that we'll have to do. So you can write this down if you would like, but we'll go through that example here. Okay, so we're going to do example 9.7, cholesterol levels. So A dietitian wishes to see if a person's cholesterol level will change if the diet is supplemented by a certain mineral. 6 randomly selected subjects were pre-tested and they took mineral supplements for a 6-week period. The results are shown in the table. Cholesterol level is measured in milligrams per deciliter. Can it be concluded that the cholesterol level has been changed at alpha equals 0.10? Okay, so first we need our hypotheses. So we're assuming that the difference is 0, and it says, can it be concluded that it has been changed? So it didn't say greater or less than, it just said changed. So it's not equal to 0. This is our claim. Step 2 is finding our critical value. So we have our degrees of freedom, remember, is 6 minus 1, so 5. We have alpha equals 0.10, and it's two-tailed. So we go to our t distribution because we're doing a t-test. So our t, two tails, alpha is 0.10. That's our second column, and you're going to go down to 5. So our t is plus or minus 2.015. Okay, so step 3 is calculating the test statistic, and there's a little bit involved in that, so I'm going to go to a blank page to do that part. So step 3, we're going to make a table. So our before is our x bar, or x1, sorry. Our after is going to be our x2. Our d is x1 minus x2, so that's our difference. And then d squared will be x1 minus x2 squared. So we were given the table, so 210, 235, 208, 190, 172, and 244. The after, we get 190, 170, 210, 188, 173, and 228. So the difference, we're going to take the first column minus the second column. So 210 minus 190 is 20. Then we get 65, negative 2, 2, negative 1, and 16. Then we're going to square all of those. So 20 squared is 400, 4,225, 4, 4, 1, and 256. Okay, then for our standard deviation formula, I'm going to write that down so we know what values we need. You're going to need n times the sum of the d squareds minus the sum of d squared. So these are different because this first one is the sum of my d squareds. That would be my last column. And then the other one is add up all the d's and then square them. And then we have n times n minus 1. Okay, so we need the sum of the d's. So we add up all of those, you're going to get 100. And if I add up all of those, that's my sum of my d squareds. That's 4,890. So now I can substitute those values in. My n is 6. Sum of d squareds is 4,890 minus 100 squared divided by 6 times 6 minus 1, so 5. And that value is 25.4. Okay, so we have our standard deviation. Now we need to find D bar. So for our test statistic, let's write that down. Our test statistic is T D bar minus mu sub D over S sub D divided by the square root of N. So D bar is the sum of my D's divided by N, so it's the average. And so that's 100 divided by 6, which is 16.7. Okay, so now I'm going to find my test statistic. So 16.7, and we're assuming the difference is 0. Then we have 25.4 divided by the square root of 6. And for that value, I got 1.610. So I'm going to go back here. Step 3, our T was 1.610. So when we compare, we had 2.015 and negative 2.015. So 1.6 is not in the rejection region, so we're not going to reject. So 1.61 is less than 2.015, so do not reject H naught. And then our last step is there is enough evidence, or sorry, there is not enough evidence to support the claim. So the claim was in our alternative hypothesis. We did not reject H naught, so we don't have enough evidence to support the claim. Okay, so we'll do another example. For this example, I would recommend that you do this, pause the video, do it by yourself first. I'm not going to write down all of the data to calculate everything on this example in the video, but it will be in the notes, so you can look there to check your values. So I'll give you what the values are. Okay, so a random sample of 9 local banks shown in there shows their deposits in billions of dollars 3 years ago and their deposits in billions of dollars today. At alpha equals 0.05, can it be concluded that the average in deposits for the banks is greater today than it was 3 years ago? So we'll call this X1, X2. Use alpha equals 0.05 and assume it's normally distributed. So our hypotheses, we're assuming the difference is 0, but our alternative, our claim, is that it was greater today than it was 3 years ago. So when I take X1 minus X2, those are going to give me negative values because we're saying that it's greater now. So if I had 2 and then 5, 2 minus 5 is negative. So this has to be less than 0 because we're assuming that it's greater now. So this is the claim. The critical value, degrees of freedom is 8 because we have 9. This is one tail. At alpha equals 0.05. So our T, go to your T distribution. We have one tail, 0.05. That's the second column, and go down to 8. And you're going to get 1.860, but it needs to be negative because it's a left tail test. So our picture is negative 1.860, and we want to know if it's in the rejection region. So step 3 is our test statistic. D bar minus mu sub d over SD divided by the square root of n. D bar is the sum of all your differences. I got negative 1.081 for that, minus 0. And then for the standard deviation, I got 1.937 divided by the square root of n. In my table, I rounded all of my differences to 2 decimal places. And then when I squared them, I did 4 decimal places. So make sure you did that, and your values should give you that. Okay, so then that gives me a t-value of negative 1.674. So negative 1.674, when I look up here, would lie on the right. So we're not going to be able to reject. So step 4, it's outside of the rejection region. That's greater than negative 1.0860. So do not reject H naught. And then my 5th step, there's not enough evidence to support the claim. Okay. Again, in this one, the null hypothesis can be different. You can say that we say a diet will lose an average of 3 pounds a week. So it's not always going to be 0, but for our purposes, it will be. And then example 9.8, we're going to find a 90% confidence interval for the data in example 9.7. And so in your homework, it'll do this too, because you have to calculate SD and all of that, again. So we're going to use the stuff from the first example that we found. So our D bar in the first example was 16.7 and our T was 2.015, times our standard deviation 25.4 divided by the square root of 6. And so we'll get 16.7 plus or minus 20.89. And then to evaluate that, I'll get negative 4.2 is less than mu sub d is less than 37.6. So mu sub d, what we do to figure out if we're rejecting or not, 0 is in the interval, so we don't reject H naught. So it's likely that the difference is 0 because it's in a 90% confidence interval. And something just to review here, the more confident we are, so if we make it a 99% confidence interval, then the interval has to get bigger so that we can be more confident that it's in that interval. So you sacrifice something for making it bigger. All right, and that is it. So let me know if you have any questions.